Let's see, we're live on YouTube. Trying to stream on LinkedIn too. Got an error. Let's see if we can get it going. I know we're also a minute or two early, but wanted to get the stream going while people join in. As you join in, say hello in the chat. It's always fun to see who is here, maybe where you're watching from. If you have any interesting projects that you're building, or maybe why you're interested in learning more about pipelines and object detection today, let me know in the chat. And I'll share links probably a few times. I'll wait a minute before I share links for the code. So this is going to be some slides and then hopefully a lot of hands-on if you want to follow along. So I'll share the code probably a couple times before we really get going. Links to everything is in the description as well. So you should be able to find all these in the description, or if you're watching the recording later, you can find them there as well. I'll share them in the chat though right now too. So one is if you want to follow along, there's probably just one account that you don't already have, which is a Union account. I'll talk more about this later. It's free to sign up. There's no card required. You get $30 of cloud credit. So we're going to be building a pipeline in that platform that's going to allow us to enable like modern practices like caching, resource containerization, and utilization per task, which will be cool. So we're going to train an object detection model. I'll talk a little bit about how you can build your own data set for this too. So after you go through this workshop, hopefully you want to go make your own object detection model on your own data set. I think that's really fun. But we're also going to be building a modern AI pipeline for it. And we'll talk more about this as we go. But that's why you need the Union account. And I'll talk more about Union in our open source Flyte, Flyte, that's used by thousands of companies in production to build their AI pipeline. So hopefully, if you've done object detection before, the pipeline part will be interesting. If you've built AI pipelines, the object detection, computer vision part will be interesting. If you've never done either, hopefully this will be a good introduction to building modern MLOps pipelines and object detection for computer vision. So again, I'm going to give it a minute or two before we get going. But as you're waiting, go ahead and sign up. And then also I shared the GitHub link for the code. I know also when I'm at a talk or something, I like to go ahead and poke around at the code while the other person is talking. So it's going to bring you to a GitHub repo like this. To run this more easily, I recommend just running this in Colab. This is what I'm going to show today, Google's way of hosting a Jupyter notebook. I'll share the direct link to this as well, but you can just always hit that open in Colab button on the GitHub. And then there's a couple cells that kind of run setup. So this one, and then once you have a Union account, a Union service account, you can run this code cell, and this will authenticate to this. And then you could go ahead and run all the other code cells. You will get an error if you run too fast on the later one, because there's one that's expecting a trained model, and our first pipeline that we're going to run is train the model. So if you run a little bit further down, again, don't worry, I'm going to go through all this later. Just waiting for people to join. If you run one way further down here on pulling down a model and running inference with it, you might get an error, but you should be able to start running this all if you want to, kind of while I'm going through the slides. But again, I'll go through setup again when we get here. See, a couple minutes in, someone said hello, welcome. Where are you watching from? What are you building? Are you building something interesting or learning? Someone asked, are you live? I hope you can see me. Oh no, this is live. I was like, I hope I'm live. No, this is not recorded. It will be recorded, so you come back to this, but this is not a pre-recorded webinar. It's me actually live here. So definitely talk in the chat. I will keep an eye on it as we go. I know sometimes there's something like a 30-second delay between like me talking and you seeing it. Sometimes there's for streaming. So it might seem like I don't see it for a little bit, but I will try to answer all the questions that I see in the chat. If it gets really busy in there, which is awesome when that happens, but if I miss your question for whatever reason, feel free to ask it again. And then I'll have time at the end to kind of catch up, or I'll have moments where I pause and try to catch up as well. So again, these links are all in the description here as well. And if you're watching the recording later, you can find them there. I will also just share, there's a Slack link, which I won't be monitoring during the workshop, but if you have questions later, or you want to introduce yourself to the community, I think there's almost 5,000 people in there. Feel free to join it, say hello, and stay connected in there as well. Someone said, I seem like a very fun person. Well, hopefully. I try to be somewhat fun. All right, so again, share the links. Let's get going. I'm gonna go through slides and then we'll go through the code. If you want to jump into the code, like I mentioned, I keep seeing people joining, so that's why I'm kind of reiterating myself. If you want to go ahead and jump into the code, you can find the links in the chat or in the description. So today we're going to build a computer vision object detection pipeline. We're going to use a model called FastRCNN. The R there stands for region, and then CNN is convolutional neural network. I'll talk a little bit about these as we go. But we won't dive like super deep into convolutional neural networks or like an intro to deep learning. But you'll be able to run all the code. So if you've never done any deep learning before, don't worry. You can always go back and like pick apart this code and dive deeper into those subjects later. So we're going to build a pipeline today that's going to have like modern best practices like caching, local development, resource allocation, and containerization per task. So we'll talk more about this kind of as we go, but it's going to be kind of a state-of-the-art modern type of pipeline for training our object detection model. And then we'll also show how to run that object detection model on images, on a video, so you can actually produce a video like this. And then I'm hoping that you'll want to bring in your own data set and make a cool video like this on your own data. We'll also go a little bit into how you could like pull this model down, run it on an edge device, something like a Raspberry Pi. And then I'll also show a deployment version in Union 2 on the cloud that can access your webcam and then take a photo and then do object detection there. So we have a lot to cover. Again, you can only go so deep in every single topic in the hour and a half or so this is going to be. But yeah, you can always dive deeper in those topics later. And again, ask me questions in the chat as we go. A tiny bit about me. My name is Sage Elliott. I work at Union AI. Again, we'll talk about this later, but this is going to be the platform that we are going to use to run today. Again, there's a free account for serverless, no card or anything required. You get $30 in cloud credit, which we're going to use just a fraction of that for some GPUs to train our model today. I live in Seattle. I don't know if anyone else in the chat happens to be in Seattle. It's always fun to kind of see where people are watching from. So let me know in the chat. And previously, I've done a lot of work in computer vision, ML monitoring, evaluation, kind of MLOps in general. And then previously I did a lot in like hardware, some IoT and robotics as well. If you want to connect with me on LinkedIn, I like to share, hopefully, well, I think it's cool, a lot of cool stuff in there, but kind of more about these events. And I also run an AI book club right now where we've been reading a new book every month. And that's been really, really fun. And you can also get details for that in the community Slack that I shared previously as well. Just putting that in the chat one more time. And I see a lot more people joined in. Hello, everyone. Say hello in the chat, where you're watching from, what are you learning or building? Actually, perfect timing. Oh, no, I thought I had that on my next slide. Yeah, say hello in the chat, a little bit about yourselves. It's fun for me, but I think everyone else watching too, to kind of see like what people are doing or where people are tuning in from. So what is object detection? So here's an example of it running on a video here, and it's kind of hard to see the text in this GIF. But basically, we have two different classes of objects. These Flyte stickers, so this is the logo for our open source Flyte, F-L-Y-T-E. And then Union stickers is our logo. And basically, I just trained an object detection model to detect these two classes. But it's not just doing classification. Like if you've looked at classification or just computer vision in general, you might have seen like the kind of classic dog or cat example where you give it a photo and it says like, is it a dog in this photo? Is a cat in this photo? Instead of just saying is something in the photo, we're actually saying it's in there, but also we can draw kind of these approximate coordinates inside this bounding box of where it is. This really opens up the door for a lot more advanced computer vision use cases. Like now you can count how many are in a frame. So you could be like, you know, how many birds or something like that are in your yard is a fun use case I've seen people use object detection for. Or you can now start tracking things. So if you want to count like how many cars are driving in a road or past a road or entering a garage, you can use object detection as a kind of the foundational layer to build out a lot of these advanced use cases. You can also see where it is. So if you're navigating something like a robot or a self-driving car or a drone, now you have an understanding of where something is within the frame, and you can do something like go towards it or not hit it. And yeah, like this is a foundational part for a lot of really cool computer vision use cases. And also I'll throw in the chat, has anyone built any computer vision model before? Actually, object detection, classification, visual language models now are really cool as well. Has anyone kind of trained your own or built your own before? And then just kind of quickly noting for data annotation for object detection. So I built this little data set that we're going to just use as the demo today, but you can go build your own data set. There's a whole bunch of different free tools or tools of different trials that make it even easier to label. But you want to have a data set, and then you're basically just drawing these bounding boxes around those objects in the frame. I use Label Studio here, but you could look at CVAT, Label Box. There's a whole bunch of other ones. But I want to quickly note, so our data set today is pretty small. It's just meant for this demo. You usually want to have pretty big data sets when you're building something for production, but you can start small and then keep adding data to it later. But these are things that are going to really determine how good your object detection model is, like the amount of data you give it. A big thing is the amount of variations too. So we'll actually see this a little bit later. We're going to train our model, run it on some stuff that it wasn't really trained in, and it's probably not going to perform as well. But you want to have all the different variations of like lighting or orientations or different types of backgrounds and stuff like that in your data set when possible. You want a proper label, so make sure that the bounding box is drawn pretty tightly around the object, not super big or not inside the object. If you miss unlabeled objects that you're trying to detect, it can also really throw off your computer vision model. And then typically you want to build 3 data sets, one for the model to learn from, which is training, one for as it's training, you can kind of look at how it's performing on this kind of separate validation data set, and you can adjust hyperparameters. And then you have a test data set where kind of after that's done, you feel like the model might be good, then you can run the model on a separate test data set and see how it performs there. So again, some annotation options. I use Label Studio. It's a pretty lightweight open source version that's really kind of easy to use. Doesn't have a ton of bells and whistles in terms of features. They have a parent company called Human Signal, which I think does. So like if you've seen stuff with vision language models now, there's probably there probably is an open source version that does this too, but you could give it a prompt to label all the things in that image, and it might do like 80% of the work for you, and then you go fix it, which is really cool and can save you a lot of time for data annotation. Faster RCNN model, which is what we're going to use today, is a 2-stage object detection model. So it uses a convolutional neural network as a background, like a ResNet. Today, we're actually going to use a lighter weight convolutional neural network called MobileNet. So you could actually run the model that we're going to train today on something like a Raspberry Pi without even doing a lot of optimizations. It can run at a decent frame rate per second, but then you could do more optimizations to get it to run. And just kind of how these work at a high level is you have this region proposal part. Region proposal network is what RPN stands for. It's going to run on an image, kind of generate some loose bounding boxes where it thinks an object is that it's trained on. And then it's going to classify that region and then do a tighter bounding box regression and hopefully get a good sense of where the object is and draw the bounding box around it. So the 2 stages, like RCNN, they're usually higher accuracy, but they can be a little bit slower than a 1-stage model. So you can look at like single shot detection or YOLO. Those can be a little bit faster and a little bit lighter weight. Depending on your use case, there's a whole bunch of different models you could choose from. We're going to use this one today. And the process of what we're going to do today is going to be very similar if you use one of the other ones. So you could swap out, like in PyTorch, you can import a single shot detection model instead of the RCNN. And then a quick note on MLOps and kind of ML pipelines. Real quick before I get in the note, I want to catch up on the chat. Said, hello from California. Thank you for hosting it. Awesome. Thank you for being here. Someone said they're from India and they're a newbie in the coding space. Well, welcome. Hopefully this will be a fun introduction to kind of building computer vision models and MLOps pipelines. They said they have interest in AI and could provide a roadmap. I could talk more about that later, but hopefully, again, like this will be a good intro. Someone said, not really. I think this is the answer to the question of if you've done stuff with computer vision. So again, I saw more people join in. Welcome. We're going through slides, and then we're going to go to the code, which I shared the code in the chat, but it should be in the description as well. Someone said, not really. They haven't done stuff too much with computer vision. They did not try object detection. Awesome. Well, I think object detection is really fun. So a quick note on MLOps, and ignore this bit.ly link at the bottom. That's from a different workshop I ran that I stole the same slide from. But I will be rerunning that in a couple weeks if you want to train a large language model versus a computer vision model. So MLOps is a set of practices to use with tools to kind of deploy and monitor and maintain your machine learning model in production. And then I like to use the terms reliably and efficiently. And usually also with that comes like scalable if you're building something really big. And efficiency can mean like fast and also just resource efficient. So it could be like cost efficiency, but also like engineering time efficiency. Typically, this is kind of a very scaled down pipeline, but you're going to probably have all these steps. And again, in the chat, let me know if you've built out a pipeline, maybe with some of these steps before. Typically, you're going to have some sort of data collection phase, or you're going to get the data from somebody. From there, you often might also have some sort of pre-processing on that data. Then you're going to train a model. You want to evaluate the model. Then if that model is good enough, you want to ship it. And this looks very different depending on what your use case is. This could be down to an edge device on a farm without any internet connection. This could be in the cloud where you have a stable internet connection and you can kind of easily get a monitoring feedback loop going in there. Once you have this model deployed, you want to monitor it in some way to understand that it's performing as good as it could or as good as you want it to. And when something bad happens, like if it's not performing as well, you usually want to fix it. And a lot of times that fix comes from getting that new data from production and then kind of doing this whole loop over and over again. So a big problem that comes up is data drift, where let's say if you trained a model on cows in the summer in a farm, this is actually something I've worked on in the past. So that's why the use case comes to mind for me. So the background on those cows would be all like, let's say green grass or something like that. And then let's say the winter comes and now either the grass is dead and it's brown or there's snow on the ground and it's white and it's hard to kind of see the cow versus the green background. That's an example of data drift. So the data no longer quite looks like the data that was coming that was used to train the model. And chances are the model's not going to perform as good on it if the data doesn't look like the things it saw when it was learning. So typically you're building this whole loop in there. And during any of these other phases, you might go back to any of these other points in time. So like as you're training the model, you're evaluating it. It's not good enough. You might need more data, or you might need to adjust hyperparameters. So usually you're rerunning these kind of pipelines over and over and over again. And when you're doing this at scale, like in a big company or a small team, and again, you're just doing this a lot of times, there's a lot of opportunities to, again, save cost from being like a reliable pipeline, but also your engineering time and cost for compute. And we'll talk more about this a little bit later, what some of those top things are. But imagine doing this a whole bunch of different times, not just once. Like if you've been playing around with machine learning models and you train something in a notebook, typically you're doing way more than just that when you're putting stuff into production. Fortunately, there's many tools that make these steps way easier for like ML monitoring, training, validation, and stuff like that. You've probably used some of these libraries before. And we want to tie all those tools together in a workflow, which is kind of the core of building those pipelines. And again, I'm using the term here, building a reliable and efficient workflow for your AI application. So some of these I kind of already mentioned. Scalability, you want to think of how can you facilitate the scaling of your workflow to handle really large data sets and complex models. So you typically don't want to be having that compute spun up until you need it. So you can have that, so you're not paying for it. And then when you need this massive amount of compute for your data sets, like if you're a self-driving car company or something, for example, that data set's really massive. When you're training new models, you want to be able to spin up all that compute, train a model, and then be able to spin it down. You want to have reproducibility. So when you rerun those workflows, like this pipeline that I mentioned, you're going to probably be rerunning this or sample or parts of it over and over again. You want to ensure that you get, those results consistently reproduced. And it also helps a lot with just collaboration against teams and transparency of what's going on in your ML workflow. Versioning. So most people have probably thought about versioning their code. When you rerun that whole pipeline every single time, you really often want to have a version of not just the code, but the data and the models and everything that went through that pipeline. This is good for any type of company or team, but sometimes it's also more required. Sometimes you actually need some compliance stuff, like in other industries like healthcare and finance. I think typically you want to be able to have full lineage of what this pipeline looked like, so you can go back and debug exactly how your model came to be. And then improved efficiency. Touched on this a little bit earlier, but you want to allow your data scientists or AI engineers to really focus on like building it, not maybe configuring a lot of stuff like infrastructure to get in production. So often when I help people set up like a modern pipeline, you'll hear things like they were going from like weeks on experimentation to days kind of thing. And again, there's just a lot of interesting little things that might sound low hanging fruit or no brainer, but if you're building an MLOps pipeline at scale, they can really, really make a huge difference in your organization. You have cost efficiency. You want to optimize the resource usage between each task. And again, also when you when you account for like engineering time and all these other things, I'll hear numbers sometimes that blow my mind. Like a company or org will start saving something like 67% or 50% of cost, which is wild when you implement a kind of modern pipeline. So just a hammer on some of the low hanging fruit things to think about when you're building out a pipeline is optimizing for local and cloud development. I even saw a big discussion on this the other day from like a major data engineering person on LinkedIn. So you want to utilize like your local compute resources more than your expensive or slow cloud, or it's slow when it's spinning up often for testing and iteration. So if you're building a pipeline like this, kind of a little example, and you want to run through and make sure that it's working, but you're probably going to have bugs when you're building it, right? And you want to debug and fix those issues. Instead of waiting for like the cloud job to spin up, like a container to spin up, and then run the code, and maybe has to even download a model first or data set, and it can take a long time. And then you get to the point where you weren't sure if it's going to work, and then you get an error. That could take like 10 minutes or more sometimes to even get to that point. So optimizing where you can actually go and run like a lighter weight version of your pipeline locally can save a ton of time and resources. So you might use a smaller model because we have pretty good laptops now, most people. You might use a smaller model, you might use a sample of the data set, but you can go through kind of end to end and make sure that the pipeline works before kicking off the cloud job. You want to leverage caching in your pipeline. So if you're doing a training model, thing like we're going to build today, we'll actually show how to enable this. If you're rerunning that whole workflow, you might not want to re-download the data set every time or do the pre-processing step every time. You just want to change hyperparameters in your training model task. Then you can just rerun this workflow and not worry about these other steps rerunning. They're going to be cached. So again, this can also save a ton of time and resources of not doing those tasks over and over again. And then task level resource management and containerization. So the big one, where if we were doing this, we're downloading a data set, we're pre-processing the data set, and then training a model. Well, for the data set tasks, we probably don't need a GPU here. We're just spending time downloading something. You don't want to be paying for an expensive GPU or hogging a GPU, even if it's on-prem, from other data scientists that could be using it. So you can task level kind of configure the resources you want for those tasks and the container you want. So you could also have lighter weight containers that don't contain PyTorch if you don't need it, etc. And then you can also look at these tasks and see, based on the resources I configured for it, am I actually utilizing all those resources, or should I kind of adjust and pull those down? And then just one thing, another thing that also kind of sounds like a no-brainer maybe, and if you've come from other languages, you might already be used to typing. With Python, right, typing isn't default, but you can implement type safety kind of into your tasks here. So this is really good for a collaboration too when you're sharing code with other people. You can quickly see in a function or a task what type of data is coming in, what type of data is expected being out. But this also kind of reduces debugging time because it's going to yell at you when you try to run it if you did something wrong in your function and you're outputting the wrong type of data. So MLOps, like we just talked about a few things, and a lot of them I think are kind of like, if you thought about it, things you might have realized, or maybe they seem kind of like no-brainer things. MLOps has so many opportunities to increase efficiency. And if you're doing this at scale in a large org or a small organization where, again, you're rerunning these pipelines all the time, which is very, very common, there's so many little things. Like you could implement just one of these and you might be surprised like how much it could save in your organization. And who likes it when you save a lot of money in your organization? Often that's like gonna be your boss or people who run the company if it's not already you. So it's actually also really common when I see people come and implement kind of like pipeline stuff like this, if it didn't exist in org, that they get promotions and often end up kind of running that MLOps org. So keep that in mind as well. If you're looking for things to increase efficiency in your company, kind of just low hanging fruit things that you might want to kind of poke around at. So today, to implement all these things and more, and to get the GPU compute to run, if you want to follow along in the code, we're going to use Union Serverless. It's built on top of Flyte, which is our really popular open source. I'll share a link to this in the chat as well. Flyte, F-L-Y-T-E, it came out of Lyft. That's why it's spelled that way, was their internal AI orchestration tool. And then they open sourced it. And then the founders of Union were the original engineers that created that project. And then they formed a company around it called Union, or you can find us at union.ai, which you should see links in the description. And we make it really easy to add all those things that we had talked about. just with Python code. So here's like a snippet. You would write a Python function. We're going to see this in action a little bit later here. Write a Python function kind of like you normally would. We enforce data typing, and then you add this decorator on top and pass in parameters like, do you want caching? What container image do you want to run on? We even have something in Flyte and Union where you can define that container image directly in your Python code. So you don't actually even have to go write a Docker file. You can write everything in Python here, declare your whole infrastructure. What compute do you want for this task? You don't have to go to any other YAML config files or any other places to basically get access to your infrastructure to do all your model training and model deployment. So declarative infrastructure, versioning. So every time you run a workflow, you get a full version of that workflow, including all the artifacts that passed between different tasks. Caching, type safety. It's super flexible. There's a large plugin ecosystem, but also it's just running in containerized compute. So most Python libraries and stuff should already work even without an official plugin. We have checkpointing. So if you want to use like interruptible tasks, you can do that. And then it's scalable. It's built on top of Kubernetes. So every single task, we'll see this in a little bit. You can define these compute resources and they're containerized, and then you can scale that up to your needs for like your training. It has a user interface and a API and SDK. So we're going to see all this in action here in a second. Oops, why is the transition weird? Yeah, so Flyte and Union's used by over like 2,000 companies. So the Flyte ecosystem is really, really robust. And take a look at it. All right, so if you want to follow along, again, here is the sign up link. There's no card required. This is the best way and easiest way to even try out Flyte right now. Just because if you're running Flyte, the open source, you have to set up a Kubernetes cluster either locally or like in a cloud. So Union serverless, even if you just want to try out kind of features in the open source, is kind of the quickest way to give it a try. And then I will, oops, this isn't copyable. This is the link to the code. And let me know if someone's trying to sign up, let me know if you could sign up. So it does take like 3 or 5 minutes to go through, but I know that we were having some sort of authentication issue with a platform or library we're using for it this morning. And I'm not sure if that was resolved or if there's still some underlying bugs. So if anyone's trying to sign up and you cannot sign up and it's been like 5 minutes, if you give me your GitHub handle, because it requires your GitHub account to sign up, if you post your GitHub handle in the chat, I will pass it on and we'll get you pushed through. So we can still get people in there. It just automatically might have a bug on a redirect thing from the library or from the platform we were using today, unless the outage is fixed now. So hopefully it is, but if not, again, let me know in the chat since I can't see all of your screens. And if you want to follow along, again, we can go to that GitHub repo. And then you'll want to hit open in Colab. And then from here, I like to save a copy in my drive, but you can run directly from here. But if you save your own copy, you can edit code and text and stuff and have your own version. You can always come back to the original one if you do break it, so don't worry about breaking it. And once you do this, go ahead and run this first code cell. This first code cell is going to, oops, let me open my copy. This first code cell is going to take a couple of minutes to run. We're using Google Colab. It's Google's way of hosting a Jupyter notebook, and it comes pre-installed with a whole bunch of common data science libraries, and one of them is PyTorch. We're using a different version of PyTorch. So actually, the part of the process here is the uninstall. So it's going to take a few minutes. Cool. So someone said the sign-up screen spins in a blue circle forever. So it sounds like the bug for the authentication thing we're using has not been fixed, which is unfortunate because I know it sounds like people want to follow along. If you post your GitHub handle, if you're okay doing that in the chat here, I can get you pushed through. I'll share it in an engineering thread and they will push you through. If they don't already automatically in a little bit, but yeah, if you can share it, I can make sure that it happens. And I apologize. Yeah, unfortunate timing for a bug when I'm running a workshop. But also, that bug I hopefully will be fixed pretty soon. So if you come back to this recording or come back to the notebook. Like you could watch me run through everything and then come back and run all the code cells yourself. Let me see if I can copy. I see someone shared their thing, so give me a minute. Perfect timing. You can go ahead, even if you haven't signed up yet, run this first code cell too. So this is going to take a few minutes anyway. So while this is running, let me try to get people's GitHub handles. If you share them in the chat. Got one. Thank you, Jeremy. I passed it on. If anyone else has any they want to share, let me know. Again, I apologize. It's out of our hands. It wasn't us pushing bad code or anything. It's just an outage for something we're using. And again, if you can't run this live right now, hopefully you can come back, I don't know, in a couple hours or something like that, or tomorrow, and that bug hopefully is fixed or the outage is gone. So while I'm also installing this stuff, and again, share the GitHub handles, and I can hopefully get you pushed through, I'll go a little bit more into what we're going to build. So we're going to come away with various things of like being able to run an object detection model on video like this. And we'll also show how to host it in an actual web application, which I think this spun down, so I'm going to have to refresh it. While that's refreshing, I'll show you a little bit of the Union UI. So if you are able to log in, or we get you pushed through, you'll be able to log in. You'll get to a UI that looks like this. Yours won't have all these runs because you haven't run anything yet, probably. I'm going to go to my execution tab, and I can see kind of here's a whole list of my workflows that I've built. I can click in this latest one, which is me testing this workshop again this morning. And this is the pipeline that we're going to build today. So we're going to download a data set. This is one that I annotated and I'm storing on Hugging Face Hub, which is a great option to store your data set. We can see I can click into each of these nodes. You have different views. I'm going to use this graph view and click into these nodes. And then I have a version for every input and output of these tasks. So again, this is really good for Lineage. I can come back anytime, see where this model came from, and kind of debug or just understand what was going on and what created this model. I have inputs and outputs logged. These are URIs where the data lives for that. And then we're going to download a model. It's going to be a model from PyTorch, and I'm going to output it and then pass it into train model. And then in training model, we have our inputs and outputs. We also have something called a deck, and I'll show how to enable this in Python a little bit later. But we can embed any visualization or really any markdown or HTML that we want. So here I have kind of the training value, like our loss and our accuracy, and what it looked like at the last epoch of our model. And also, one thing I always do, especially in computer vision, but it's good for any type of data, is read in your data set. And with computer vision, object detection, you have images, and then you have this JSON file that we can look at later that contains coordinates for those bounding boxes. And it's very common to accidentally make some sort of mistake where you read in the images wrong or you read in the JSON incorrectly. And this has happened to me so many times, even just the other day when I, again, thought I was doing it correctly. So I always have some sort of step where I can make sure that like I read in the images and then bounding boxes are around the things that I expect them to be. So really, really good to have kind of this kind of extra step to just make sure that your data was read incorrectly. After we train our model, it's going to go to this evaluate step. And this also has a deck in here where I show some predictions on the model, or sorry, on the images. And then we can see like class 1, class 2. We'll talk more about those a little bit later, but those are the correct classes here. And then we can see the bounding boxes are drawn on the items pretty good to me. And then we actually have this evaluation report. So we get the mean IOU on a threshold of 75. We'll see what this looks like in action, but basically the threshold is something we give it to say only draw predictions when you're like 75% sure that the object is there or the class is there. Otherwise, if this is really low, you'll get bounding boxes, usually in most object detection models, kind of all over the place. And I'm only calculating IOU on that, which is an intersection over union. And that is a metric that is good for object detection, where instead of just classification, where you can say, yes, it got the class right, or no, it didn't, which is kind of easy to understand. IOU or IOU and average precision is a way of measuring how well these bounding boxes are to the ground truth. So if I don't have the ground truth drawn in here, but imagine if the ground truth label was very close to this red box, but it's not exactly right. This might be like an IOU of 90. If the red box was like really way bigger and the ground truth was, way smaller, the IOU would be less. So you basically IOU of 1 is a perfect score, and we're in the 90s, which is pretty good. So if it was 1, then that would mean the predicted label was drawn exactly where that ground truth label is, the annotated label that we did. That would be an IOU of 1. And then the worse it is, the lower the number gets here. And our accuracy score, it got none of the classes wrong. That's why it's 100 there. But with object detection, often the more important thing is kind of this IOU score to measure how well it is. Someone asked, can they send the GitHub handle in the Slack channel? Yeah, I am in the Slack. So if you joined the Flyte Slack, I'm in there. My name should just be Sage Elliott. You can DM me your GitHub handles there as well. And then once we have our trained model, this is going to be saved as an artifact, which again is also version. And this is in our artifact tab here. I could embed and add kind of a card. Maybe having the evaluation metrics would actually be really good in the card here. But I can click in to this lineage tab, see exactly what workflow this artifact came from, and then click into it anytime, and then go back and again have that full version, not just the code, but actually all of the metrics and the artifact versions as well. And inside this deck, you can click around. You can even see source code is in here, but you can pull all this down in the SDK or from the API as well. So you don't have to use the UI. You can easily relaunch this. Again, we'll see this in code, but you can relaunch from the UI, change hyperparameters here. So I've actually seen some people build like a pipeline, but then you might have a domain expert or something that wants to look at output and then adjust hyperparameters, but they're not like the AI engineer. You can do this all directly from the UI as well. And I'm just going to pass along B's GitHub handle. I think you gave me an email. Do you have a GitHub handle you can pass through? I think I might need to pass on the GitHub to people. Let me know, and I will pass that over. All right, so I'm going to go back to the notebook. Mine has done installing here. If you were able to sign up, or when we get you unstuck here, again, unfortunately, timing from the outage, we can run this union create login serverless to authenticate basically this whole notebook, but you could also run this on Raspberry Pi or any hardware, and you would authenticate your device here. And then click here, and then hit next. And then now my device is successfully logged into serverless. I got that person's GitHub account. I'm just going to pass it on real quick. And I'll mention you got stuck at spinning wheel. And thank you for reporting that and letting me know, because I wasn't sure if the outage was still going on. All right, so I'm going to get back to the notebook here in a second. Let me just make sure. All right, so I'm going to go through all the code. And again, I'm going to go kind of fast here, but you can always come back. And also, you have all this code, so you can go run this at your own pace. But I also want to make sure that we try to get through this pretty fast as well, just for the workshop purpose. So go ahead and run this code cell if you are able to log in later. And I'll talk about what this is doing. This is running some code, obviously. This, for me, because I've run this before, it's going to skip building a container image. And I'll talk about the container image here in a second as well. What we're doing here is calling union run, and then we pass in this remote flag. This is saying we want to run it, in this case, on union serverless, because that's what we authenticated to. And then we can see we're calling this from this workflows folder. There's a train frcnn, or RCNN pipeline.py. And then this is a specific function in there. And then we can pass in a parameter here, the amount of epochs, the amount of times we want to look at our data set for our model to learn from. For me, it says execution running on remote. Image fine-tuning was already found. And I didn't update the name for this. I should give this a RCNN name, not a fine-tuned QLoRa. But that image was already found, so it's skipping building. If you're running this for the first time, it'll probably take 5 minutes or so for it to build the image. And then you'll get this part where it says running execution on remote, and then you get a URL here. And if I open this up, this brings me back to my pipeline, but a new version of it that's running. And we can actually see that for me, download dataset and download model, those are actually read from cache. So if you were here for the slides, talk about caching our pipeline. Every time I rerun this, I don't really want to rerun these tasks themselves. I just want to look at kind of our model training piece here, or sorry, I want to run the model training and evaluation piece. I don't need to re-download the data set if it hasn't changed. Let me just move this over so I don't get lost as much on it. All right, so where does this code live? In this code setup, or sorry, in the setup cell that we ran above, we cloned in a GitHub repo. So if you're following along in Colab, you can click this little folder icon. And sometimes you need to hit this refresh button. And we can see that there's this folder now. This is the GitHub repo we cloned. We have a workflow folder and a task folder. So this is kind of where most of the code lives that we're going to run. And if you want to, you can double click on this and open up that code file. But I've made it a little bit easier to follow along for the workshop. And I've put all the code in code cells here. So even though we're already running it, it's already downloaded, you don't have to run any of these code cells with this write file. Write file is a magic function in Jupyter that will overwrite that Python file that it has with the code that's in here. So this is just kind of a duplicate of what we've already downloaded. So you don't need to run these code cells. You only need to run the ones that I think I put a hand emoji in all of them because that code's already downloaded. But to make it easier to follow along for the workshop, I have the code directly embedded kind of in the notebook here. So we'll just talk about kind of imports as we use them. This is the workflow that we specifically called in that workflow folder. So this is the path of where this lives too. So under workflows, we have train, frcnn, pipeline.py. And then we have this workflow decorator. This comes from the Union or Flyte library. And a workflow is basically this whole thing of like this collection of tasks and the flow of data between those tasks. So here we have all the ones I mentioned: download data, download model, train model, etc. And we're defining, okay, we have this task that we imported in, and we'll show the task code here in a second. But we want to say we called this first, and then we got data from it, and then we pass that data to this other task, which is train model. When that's done, we pass the train model and also some of the validation data set from here to this other task. So we define a workflow with these tasks, the collection of tasks, and the flow of data between them. So here is our workflow function. We have parameters that we can pass in and some defaults here. So the default amount of epochs is 3. Again, an epoch is kind of the amount of time that your model is going to look at the full data set for learning purposes. And then we imported tasks from here that live in the data folder, or sorry, in the task folder. And then I have one called data.py and model.py. And I'm importing a few of them from each one there. So we have data, Hugging Face, download Hugging Face data set. And then that gets assigned to this variable. And then we pass that variable into this verify data annotation and to the train model function. Again, these are all imported tasks we'll take a look at here in a minute. And then we have the evaluate function. And then this is commented out, but if you're interested in saving your model outside of a Union artifact to like Hugging Face Hub, you could uncomment this, and there's a task that will pass that model out and save it to Hugging Face Hub. And then we ran this command above, but to run this, you run you do union run remote, and then again the path to that Python file and the function or workflow function that you want to call here, and then some of the parameters that you can pass in, you can update here, even though we have most of them. If not, I think we have all of them here as default. And then also, if you want to run this locally, which we're not on a GPU instance here, so it would take a long time or maybe even crash, you can remove this remote flag. And then this is how you can iterate on that workflow locally, again, maybe with a smaller model, smaller sample of your data set. And then you can kick off the cloud job by just adding that remote flag. In the task we'll see in a second, we're going to be running all of them on a specific container. So every time a task here, if I go back to this view, every time this runs, it spins up a container with a specific amount of compute to run the operations that we put in there. And we get that by defining containers. And here's us using image spec. Like I mentioned, you don't have to write a Docker file. You can actually define this all in Python now with image spec from Flyte. Give it a name. Again, I should update this name to be like the fast RCNN name. And then we're going to look at requirements.txt. That's going to be all the Python packages that we want to download. We want to install all these if they can, like the version of PyTorch to run on CUDA 11.8. So we can actually say, go look at that and pull in that specific version, build that image on Union. So it's going to build in the cloud in Union. We don't have to build it locally and pass it anywhere. Again, it's kind of all handled automatically. You can pass in other packages as well. So not just Python packages, but if you need like a C++ builder, I think we needed this for this one to run OpenCV later. But also if you're doing stuff like quantization with models, you can do it there as well. And then we have our requirements.txt. These are just the requirements for using a specific version of PyTorch, Torch Vision, etc. And then we have our first task here, which is data.py. This is going to be just downloading the data set. And this is what a task looks like in Flyte or Union. We saw a preview of this in the slides, but we have our function here, our Python function, that probably is pretty similar to how we would write it anyway in Python. And then we're adding this task decorator. And this is where we put in those special kind of parameters that enable things like, one, this is the container image that we want it to run on. So we looked before, it's installing specific versions of PyTorch, etc. Other environment variables. That's going to spin up every time we run this task, and we're going to use that container image. If we want to enable deck, we hit true, which I think in the download data set, I actually don't do anything with the deck here, but I accidentally enabled it anyway. And then we have cache is equal to true. So we saw when I reran that workflow myself, it didn't rerun this task because it's cached. Give it a cached version, so you can change this version if you want to roll back to a specific version of that cached data set. And then we have the important thing of requesting the exact resources that we want. And so we'll see later we can add in a GPU when we get to training, but just for downloading, we're only using CPUs and a light amount of memory. So we're really not paying a lot for compute when we don't need it. And then here's our Python function. It's going to take in a repo ID. This is, again, a Hugging Face data repo. And then it's going to save it to this local directory called Dataset. And then I have a little option in here because the way I save my dataset in Hugging Face is it's actually in another folder. So I have this kind of subfolder option just for us to kind of look in there and then pull that data out. So we're going to create the local directory if it doesn't already exist. And then again, from the snapshot download from Hugging Face Hub, we're just going to read in that repo and save the dataset locally. And then we're going to pass it out of this task. So one thing interesting, if you're kind of newer of working with containers, is every one of these kind of nodes or tasks is a container where by default spins up that compute. You could do something in there and then it spins down. And so if you haven't developed with containers or on Kubernetes before, it could be a little bit of a mind shift to think about where does my data or the things I do live after it spins down. So by default, if it just spins down, you don't pass any data out of it. It's not going to be saved. So when you pass data out of a task inside Union or Flyte, by default, it's actually saved to like a blob storage. So you can access it later in these other tasks. And we have specific file types like Flyte directory or Flyte file that's going to serialize and deserialize the file or directory type. And then again, this gets saved to like a blob storage that you can access in other tasks, or you could query and just download it yourself. So we kind of make it easy to develop on something like Kubernetes and containers without it feeling like you're developing on Kubernetes and containers. Then we have our visualize data task. This is the task where we read in the annotations and images. So we're downloading the data set that we downloaded in the previous task. And then we're loading in this train JSON file, which again, we'll look at this later because we're going to download it locally in our Colab notebook to run something on it. So we can take a look at it later when we download it. But basically, this just contains the image names and then the bounding box coordinates for those images. So we're reading in this train JSON. And we're just taking the first 9 images and basically plotting out what we saw in this task. So if I open this up real quick to show, we have this deck. And inside here, we have these 9 images, and we're plotting out the annotations from. So these are the ground truths that we annotated. The model didn't do these predictions. This is what we drew and then exported, and we're going to train our model on it. So with the deck, if I go back up and actually look, we said we enabled our deck here. Again, we just have a light amount of resources here. And then here I am creating a little HTML report, embedding those images. And then I'm appending them to the deck. And then I'm inserting it in position 0. So it's the first tab. Now we get to the little bit more exciting Python file, which is going to be, again, taskmodel.py. Again, you can navigate here, or if you download the model locally, you can look at all the code here as well. Again, we'll just talk about kind of stuff that we use, not in the imports, but a little bit later. So one thing is we are defining an artifact, and I think I do have this on purpose twice, I think, where I'm taking the base model and then our fine-tune model, and each of these is going to become an artifact. I forget if I actually do save the pre-trained model. This is how we define an artifact in Union. So it will show up in this artifact tab. That, again, makes it really easy to share across teams or to other workflows. So we'll see later, this becomes an artifact, and we can just call artifact name.query, and it will bring in the latest version automatically. But again, these are all version 2, so you can pass in a specific hash or number and then pull in any other iteration that was there previously. So first, we have our download model. Similar to what we did before for download dataset, we don't want to download this every time. This is a pre-trained model from PyTorch in this case, but again, if you're using like LMs, this could be a pre-trained model from Hugging Face, and you don't want to download it every time because it's really big. This is actually a fairly lightweight model, so it wouldn't be too awful to rerun every time. So we have our download model from Torch Vision. We are importing faster RCNN with a MobileNet backend, so we can swap out kind of different convolutional neural networks for our different object detection models. Almost any of them, actually, not just faster RCNN, but if you do use like single shot multi-box detection or YOLO, you can also swap out different models here. So like a ResNet 50 is, I think, often the default, which is a more accurate model, but it's heavier weight. MobileNet might be a little less accurate, but we can have it run on lighter weight hardware. And then we're bringing in these pre-trained weights too. So the model was already trained on, I think it was the Coco dataset, which contains a whole bunch of images. And basically, this model is already pretty good at detecting objects and edges and stuff like that. And then we want to take this model and then fine tune it on our data set to basically just classify those things that we have in our data set. And then we're specifying our save directory for the model path. And then we're going to return it as an artifact that we can pull into another workflow. So then we have our train task. And the only big difference here is we are now upgrading our hardware. So we're, again, just in our code here, passing in the hardware that we want this to run on. So we have 2 CPUs, 8 gigabytes of memory, 1 GPU, and then this is our train model function. We have some parameters we could talk about as we use them. We're basically just taking in the model file from the previous task, the dataset file from the previous task. Then we pass in the number of epochs, the amount of times that we want our model to look at the full dataset. Number of classes. So in this case, we are doing those 2 different types of stickers. So it's 2. But if you're running this on your own data set, keep this in mind. If you're only detecting one thing, you would have 1 here. And then you would have 3 if it's 3 classes, etc. And then we are going to pass in a confidence threshold. So I had mentioned before talking about like IOU or average precision. If you don't have this, it'll look a lot lower. And that can be a good metric depending on what you're trying to do. But I like to add in a confidence threshold to understand how well my model's performing when it's trying to predict like a 75% confidence on a specific class. This will give you kind of a more realistic IOU return, most likely, depending on your use case. Then we're going to validate every step in this case, but basically we're going to look at our data set and then also run predictions on our validation data set. So again, in deep learning, you usually have 3 data sets. Your training that the model actually looks at, a validation that you look at as your model's training, and then a holdout kind of test data set that you use later. Then we have our number of classes. So again, we passed in 2 with most object detection models, but you'll want to look at documentation when you kind of import different ones in. They actually will use the amount of classes that you have plus another one. So it has a separate class for the background as well, usually. So it's like the two things is trying to draw bounding boxes around in this case, and then one that it's not, which is everything else in the background. And adding different backgrounds is a big deal for your object detection models and your data set. For example, just having, like when we run it later today, if we run predictions with a different background it's never seen before, it's very likely to get confused and think like I'm going to hold up a sticker and run a prediction and my face might be in it, and it's very likely it thinks my face might be something that is one of the objects because it's never seen a variation of it before. So you might have done a good job of telling the model what something looks like that you're trying to do, but you didn't do as good of a job of telling it what stuff doesn't look like. So you want to add in all these different variations usually. Let's see. Just setting those variables that we already passed in our function. We're going to look and see if we have a GPU device. So basically saying, is CUDA, if CUDA is available. CUDA is kind of the programming language for GPUs from NVIDIA. Otherwise, it's going to use the CPU. Then we're going to download that data set. We're going to make a directory for that data or the model if it doesn't already exist, or if it does exist, either way. Then we're just going to read in the data set here, and we're going to read in the train JSON. And then just noting here, this is fine for our demo today. I'm reading in the train JSON here for the validation data set, which is you definitely shouldn't do in production because it's going to be validating how well the model's performing basically on the same data it's learning from. I need to make a separate data set for this, but I did not have time. So we're kind of cheating today, but just keep that in mind for your actual use case. You want to have those 3 separate data sets that I talked about before, but actually just have one. And we're kind of cheating a little bit here. We'll get results on actual videos, but when we look at metrics, it might seem really, really high because we're basically looking at the same data set that it was learning on. We're going to load in that pre-trained model. And then this is really common in object detection or classification. You would load in a pre-trained model like we had talked about before. That was the faster RCNN for object detection. By default, again, most of them are trained on the COCO dataset or come kind of, come with those weights and object detection head. That just means, I think of the COCO dataset, there's like 81 different classes. So you might have seen this before. Like if you've seen an example of object detection running, it might be able to detect like bikes, people, etc. There's 81 kind of various classes in there. Basically, we don't want to predict those 81 classes anymore. So we want to lop off, like cut off the kind of detection or classification endpoint in that neural network, and then give it our own with our own number of classes. And then we're going to update just kind of these weights in that object detection layer to now look for in our case, the 2 stickers today. But if you added in a different number of classes, again, this would work for whatever number you're trying to predict. And then we're defining the parameters like learning rate, etc., for our deep learning model to learn from. And then we have our evaluate function. This is basically, again, we'll see this. We're going to go through every epoch, train our model. It's going to learn, and then it's going to run this evaluate function, which is just reading the evaluation data set, getting those bounding box predictions, and then measuring the IOU basically on them. And then here's for every epoch that we passed in. It's going to basically train our model and learn from our data set in there. So it's going to, again, read in those bounding boxes, make predictions on them, see how far off it was, update weights in the neural network, and then hopefully get better over time. And then this is the chart that we saw plotted out. If I went back to here, open this up, basically just creating this visualization of the loss and accuracy in IOU over time. And then we have our evaluate task. So we're reading in our model, but instead of training it, we basically just want to set it to evaluate. And again, we pass in a confidence threshold. So this case 75. So we're getting that IOU value of only when it's 75% confident that that class is actually there. Downloading the data set again, we're using that train JSON, but we should be using a separate test one. You're actually doing this in production. And then we're just going to plot out the first 9 images, but then we're going to basically run predictions on all of the images in the data set and then plot them out again. A lot of this code, it looks like a lot of code, but a lot of it's actually like creating these plots in matplotlib. So I think this is maybe a little less scary if you go back and kind of pick this apart. It's actually like a lot of this code is creating plots, which is really, really useful, but it does make it look like a lot more is going on here than you need just to actually fine tune your model. And even this is still creating the HTML report. So actually, if we go back and look at the evaluate model here, we open up that deck button, we get the images like before, but also we get all these metrics kind of embedded as well. So with the threshold of 75, the mean IOU across all the images that it looked at was 94. So pretty good. Again, remember, a perfect score would be 1. This is how close the bounding boxes match the ground truth. And then this is the optional one. I won't go through this, but if you enable this, this can upload a model to Hugging Face Hub if you wanted. All right, so we trained our model, or if you were able to sign in, I did pass on the GitHub handles to engineering. So I'll see if anyone got through. I can go double check real quick. But also, if you come back later and run this, and you got to this point, that means now, like, all these green check marks are there. And if you go to your artifacts tab, you should now have an artifact. Now we can actually pull that model down and run it locally. So let's go ahead and do that. First, I'm going to run this task, and this is going to pull down the Hugging Face dataset that we use for training. Again, we're just going to use like a video that's also in this, and we can sample an image and see how well our model runs. So it's just an output of downloading the dataset. And now we're going to use Union Remote, which allows us to basically do all the things we see in the UI. We can do through like Union Remote in the SDK. So if you wanted to query all the different executions or query artifacts in a specific workflow, you can all do that in Python, which is really cool as well. Here, what we're going to do is basically call .query on the artifact that we did where we fine-tuned our model. And again, .query by default is going to bring in the latest version. But if you do want a specific version, you can just update this string to whatever it is in your artifact tab. So you can see your string right here. You could copy this in and then pull down a specific version there. So every time we run this code cell, basically, like this could be on a Raspberry Pi or something, and on startup, it could automatically pull down the latest version of the model. So if I run this, it's going to pull down that model. You also have to be authenticated on here, so to pull the model down, which we already are here, but just mentioning that. So if you set this up on a different device. So it ran, and then now I should have a model that's ready to go. And we're going to run this model. I'll just go run this code cell and then talk through it. We're going to run this code cell, and we're running our model actually on a CPU. We don't have a GPU instance of Google Colab running. So it's going to take a few seconds, but it's, again, a pretty lightweight model. So we're actually able to run it just on a CPU. Okay. And what this is doing is we have this function that basically has some colors defined. And then for bounding box and label inside of our predictions, we're going to draw out hopefully a pretty looking box. And then we're only going to draw it out again if the confidence threshold is above 60 in this case, but you might want to adjust this threshold if you're getting way too many boxes drawn. And you could see that, oh, like it's 60% sure, but it's doing a pretty bad job of, or then there's ones that are really around the object that are like 90%. You can adjust this confidence threshold to get better predictions. And then we're reading in an image in this case that was just downloaded from the Hugging Face dataset. We're going to open it up. We're going to run a prediction on that image and then output bounding boxes. So I already ran this. And if I go to this little folder icon, and if I look back in again, this faster RCNN folder that should have been cloned down, we should have a new thing is output image.jpg. If I double click on this, we can see that this is our model that we just trained. The label here is a little small. I should make that bigger. But we have these bounding boxes that are predicted in, oops. Oh no, okay. You might not be able to see it, but it does say Flyte sticker there. And it says union sticker here. And the confidence thresholds on this is 99 for Flyte and 95 for union. So it looks pretty good. You can see that this isn't perfect. It's going into the sticker a little bit, but this would be probably a pretty high intersection over union anyway, because it does do a pretty good job of drawing the bounding box around it, but it is slightly in. So that could potentially be improved, again, with more data, We had a very, very small data set today, so this isn't going to be perfect. This is kind of just for demo purposes. Now we can basically take what we did here, but run it on every single frame of a video. So you can go ahead and run this. So it'll take, again, a minute to run because we're just on CPUs, not on GPU at all. So again, a lightweight enough model just to run on CPUs, which is super nice and can be super handy. We are reading a video. Again, this is downloaded from the Hugging Face hub, or yeah, it lives in this dataset folder now. And then we're basically just capturing every frame in that video, getting the width and height metrics, the frames per second from the video, number of frames. And then we're basically going to write out this object detection video.mp4. It's in the MP4 format. And then we have this function, which is running inference on that video. So we're passing in that video, making sure it has a frame. While there's still a frame left, basically run the prediction like we did on the image, but for every single frame of the video. And then we're going to yield those results out, and then we'll get a pretty looking video here in a minute. And so you'll see it'll also show up here. In fact, it's already shown up here, even though it's not done. So if you did download this right now, it would be, I think, like a corrupted video. So I want to make sure that this is done running. And I know there's still quite a few people here, but chat is super quiet. And part of that might be because you all had sign up issues and couldn't actually follow along. Let me know if you have any questions or comments or anything you think is interesting in the chat. So now we ran our video and my code cell is done running. So I'm actually going to hit download on this. So any of these files you can download. Click right there on the little 3 dots, and then you hit download. And so yeah, I should open this up, make this a little bit bigger for you all, and let's see how it works. We can see that also already, like, it's not getting this union sticker yet off to the side. In our data set, we only had full union stickers, I think, and none of them were orientated this way. So it's very likely our model doesn't know how to pick up a sticker this orientation and also a fraction of it. And with object detection, kind of like these models are really, really good, and it's all about the data that you bring into it. There's also different techniques you can do called data augmentation, where you actually can add different orientations and lighting and stuff like that automatically in here that can help with stuff like this. And we can see that it's doing a pretty good job on the sticker down below, and these Flyte stickers are doing a pretty good job of drawing the bounding box around them. And it's got the sticker on that side now. Again, I think it's the orientation and when it was a fraction of it, but the orientation is probably a big piece here because it's definitely less confident on it. And then pretty good on the other union sticker. And our training data set wasn't taken from this video, but it was on the same background. So it's kind of expected it should do pretty good. But again, if we change the background, like if this was on a much darker table or something, our model might not do as well. And then you want to take that new data and then retrain that model with it. So we got this cool video though, which looks awesome. And I will also note people love when you share videos like this on like social media. So if you're trying to build somewhat of a LinkedIn presence or show that you can do computer vision and cool stuff like that, definitely recommend posting that video or a video like that on your own data set. People usually really like it. And then also, so this won't work in Colab, but I'll talk about this code. This will run on a webcam, and I can run it locally. Hopefully it doesn't crash because I haven't done it while I'm streaming on another webcam. So let's see what happens. But basically, we are querying that model. So again, this is actually what I would run on like a Raspberry Pi on startup or something like that if I wanted this to do object detection on an edge device. And querying in the artifact again. So this is going to pull in the latest version automatically every time you run the script. Pull down the artifact, and then we are setting the model to eval to run. And then we have this little function that's processing the frame. So it's going to process the frame from the webcam, convert it to a tensor for our model to do predictions on, and then just draw out the bounding boxes, kind of like we saw before. I don't think they'll look as pretty here. We kept it more lightweight. And then this is going to run on the live video. So OpenCV has some built-in stuff like video capture. If this doesn't work on your webcam, you might have to change this from 0 to 1. Basically, there's like a port assigned to your webcam. Most webcams are at port 0, but it does vary on computer. So let me try to run this locally. And Let's see what happens. Okay, so again, I haven't done this while I'm streaming from the webcam. So hopefully this doesn't break. It's going to take a minute because it's going to query that model down every time we start the script, which again, if you don't want to do that, you just have that as a separate Python file or something. I had it set. So, oh, there we go. We're getting some results here. And again, this detection model wasn't trained with this background or a lot of these things in the background and on a very, very small data set. So I expect it to not be that great right now. But let's actually see if I pass in a sticker that I have with me. It actually does a pretty good job of drawing a bounding box around it. And again, if we knew this was going to be the background we'd be on, we'd want to have like this variation in our data set. I should be able to hit Q, kill that. And then also we can serve this in an app on Union. So let's go ahead and run this code cell, and then I'll talk about what's going on here. So in Union, we also have a feature where we make it really easy to define scaling metrics and compute for not just building your pipelines like we saw, but also for serving whole web applications or hosting models. So this could be like a model API endpoint. In this case, we're actually building a whole little app here to interact with our webcam, bring in data, and then run predictions on a model. So to define that in Union, again, we're defining our artifact to pull down. We're specifying our artifact to pull down. And then we have a separate image spec here, but you could be pulling this from like the container.py that we did before as well. We're passing a couple libraries that weren't in the other container though, like Gradio, which is a Python library for quickly building UIs, which we'll see in action here, and Union Runtime, which is specifically made for running the applications here, as well as OpenCV Headless, which is a different version that is meant for running on like servers. And then also some packages, FFmpeg for being able to run OpenCV as well. And then we define our Gradio app using this app method that we import from Union, give it a name, and then we give it inputs. So in this case, an input is the .query like we've seen before. So when this starts up, it's going to pull down the latest version of that faster RCNN model. And then we have our container image, kind of like before when we were defining tasks, but we passed it that image spec that we defined above, what port our app is going to run on. Do we want to include code from any other files? So in this case, we have app.main.py, which has our Gradio application, and that's what we want to include. This is going to start up the app, or the commands to start up the app. And then we have requests. So this will look familiar if you're here for the task portion as well. But now we're requesting this for a application, not just one task in the pipeline. So when this spins up, it's going to use these resources, and then you're going to set hard limits as well. So request is kind of like a soft request limit. I'm guaranteed this amount, but it could go higher to scale. And then limits is saying don't ever go higher than this for the application. And then we're importing a specific type of accelerator, which is the L4, which also, if you're using serverless, you have L4s and A100s in there. And then we're specifying the min replicas and max replicas. So min replicas means that in this case, we have this scale down after time delta. So after 2 minutes, it's going to go to the min replica amount, which is 0. So that means when no one is using our app for more than 2 minutes, it's going to scale down, and then we're not paying for that compute at all, which is great and really, really useful for a lot of applications, like especially if it's internal ones or ones for yourself. But with that means that if no one was using it for 2 minutes, you're not paying for that compute. But then if someone goes to visit that site, it has to spin up again. So it's going to take a little bit depending on what it has to do, like how big the model is or all the other resources it has to spin up. It could take like a few minutes to spin up the site, or a minute to spin up the site. It's usually pretty fast, but it is enough where, right, if you're visiting a website as a user and you're expecting it to be super active and responsive, it might be too long for you to wait. So you actually might set min replica to something like 1, and then always have it available for a user, but then you're paying for that compute for that replica. And then max replica, you can set a scaling metric. So if more than 2 people visit the app, then you want to spin up another replica to make sure that you can handle the traffic. So you can set all these scaling metrics, again, super easily directly in your Python code without having to configure anything, or without having to go through more complex configurations for your infrastructure. All just handled directly in the Python SDK. To run this, then you just run union deploy apps.app.py with the name that we passed it, which is right up here. And then I'll also show the app main.py, which has our Gradio application Basically, we're just importing the union runtime, and if the model exists, then use that model, the one that we passed for downloading when we called the .query when we defined our application here. And then we're loading our PyTorch model like we've done before. We have a little label map. So class 1 is union, class 2 is flight. And then we have this function that is also going to have a start time so we can actually see how fast our model ran on the hardware here. We're basically going to just read in the image, do bounding box drawing like we've done before, and then get the amount of time that it took. And then this is the Gradio part. We're launching this Gradio interface, and then we're passing in that detect object function that we saw above. The input's going to be an image, and by default, what that looks like is this. I think I might have to refresh this because it probably spun down. So I can go to my apps tab. I can see all my active apps, and you can actually see most of these are 0 of 1 because I haven't visited them in a while. So they scale down, and I'm not paying for any of that compute until they scale back up, basically. Now that I refresh that, this is restarted, or should be restarting. And also, if you get to this point later, you can click into any of these apps. Like if you ran that command from the notebook, this should already be there. And you want to click on this HTTP endpoint. In this case, that's going to take us to our Gradio app here. And now I can upload an image, or I can access my webcam directly in this UI as well. So let's try it again. It's actually, let's see. Again, it's probably not going to work super good in this background. Let's get this close to the camera. I think, oops, an error. I think that might have been still spinning up. Let's see. If you have a Gradio app, okay, yeah, so it's up now. If you have a Gradio app and you get those errors because you had the UI loaded, but the app actually wasn't loaded, I think that was the case here. So let's try it again. Click this little camera icon that'll take the photo there, and then hit submit. Let's see what happens. Hey, it actually didn't predict anything. You can see the bounding box isn't perfect here. Again, completely different, or pretty different than the super tiny training set that we had, but actually did a decent job of, but better than I thought it was going to do, a decent job of predicting where the sticker is in this case, which again, very different background than it's seen before. So Gradio is a really cool way to build interfaces like this. And you could actually now, like I know people had sign up issues, which again is unfortunate for the workshop, but if you come back and run all this and you get to this point, you've gone through and built a modern MLOps, like computer vision pipeline with things like caching, containerization, and resource management per task. And then you actually deployed this on an application, also using scaling metrics and setting min and max replica. And you actually have this cool interface that you could also share with people. In order to actually share it out publicly with people, I think I forgot to mention, if I scroll up, I don't have it in here. You have another metric you can pass in here, or another parameter you can pass in here that requires auth, and then you can say equal to false. And then that becomes a public URL, because right now you require authentication to access it. But you could pass in that parameter and then actually share this out and like use it as a portfolio piece or something if you wanted to share with other people. And I know we went through a lot in that amount of time. And like I was saying, I think some people weren't able to sign up. So again, I apologize for that. Come back later if this was interesting to you and you couldn't run everything. I hope you want to come back and go through everything. So I know there's some questions in the chat now. I'm going to go catch up on them, but also ask more questions in the chat. Also, like, this is pretty fast. I know, like, can be fast paced for people, but you have all the code. So, or maybe it's slow if you've already done all this before. So it's hard to find that balance sometimes to kind of be approachable for everyone. And I know a lot of times people say I go fast, but also some people like it. So someone said good session. Awesome. Thank you. I'm glad you liked it. Hopefully you got something out of it. Again, if you've never built like a pipeline before, I think that's kind of interesting. And if you've never trained an object detection model before, also hopefully that was interesting for you as well. Someone said Colab setup, downloaded, installed in 3 minutes. Red text. So great point, and I forgot to call it out this time. It's okay if you get a little bit of a red text error after running this setup. So So like I got it too. That's just saying that because Google Colab has these pre-installed packages, when we installed a new version of PyTorch or an older version of PyTorch that we built on, basically it has a version of Torch Audio that's looking for 2.6, but we are on 2.51. That's fine because we actually don't use Torch Audio at all in here, but it's just letting us know that we had a library that might not work anymore. But again, that's just because Colab had all this kind of stuff pre-installed, and we didn't get that version of Torch Audio uninstalled. But totally fine for the rest of the workshop. And so it said this behavior is the source. Oh, it's just more on the code thing. So that's totally fine. Don't worry about this kind of error here. So it said after doing this type of flow, how can I review how much memory and CPU cycles were used by processing? Great point. So I forget if I showed it. If not, I'll show it again. So here's like our workflow here. And there's kind of two things I'll bring up. So in serverless and in serverless, you get this option of like, let's go look at this training one because we actually use GPUs. Click into our task like we've done plenty of times to look at the deck. But now we can actually hit this view utilization button. And we can see the memory quota that we defined versus what we actually used. So we defined 8 gigabytes of memory, but we actually only used about 2. So we could bring down, or I guess at the max, yeah, about 2. So we could bring down this memory requirement down. Memory is not costing us too much here, so it's not a big deal. And CPU, we're actually using 1.5 out of 2, so that's totally fine too. But if we had defined like 4 and we were only using 2, then we could bring those resources down. And then same with GPUs, we are using GPU and GPU runtime here. And we're using the lowest tier GPU in serverless, so this is fine too. But you could look at like how much memory, or if you had put in 2 GPUs versus just 1, you can view all the utilization in this tab. And then another thing is, let me bring up real quick in a different environment. If I can log in. So inside the Union Enterprise version, so most people use us with the enterprise version of Union where it runs in your own cloud or on-prem. We actually have a cost allocation tab as well that kind of shows everything across all your projects and orgs. So with serverless, you just have a single seat, and it's meant for you kind of as, individual developer building something. With the full version of Union, you get this kind of cost allocation tab, which this is not in Flyte either. Most of what we saw, or a lot of what we saw on the AI pipeline side can also be done in the open source as well. So you can check out implementing the open source, but you don't get all the resource allocation features right now of viewing them. And the serving's a Union feature as well. And Richard said, second time here for your session. I caught up to your speed this time. Awesome, thank you. Yeah, it's always hard. Like I was saying, it's hard to find the optimal speed because some people want to go faster, some people want to go slower. I feel like fast is, I don't know, how I like to learn too. And then you get all the code, so you can go run all this on your own and pick stuff apart later as well. Someone asked, how many megahertz is one CPU? It depends on the CPU in your cluster. And let me see if that actually says any information here. So again, if you're setting this up in your own cloud, it's going to be whatever CPUs are kind of in your Kubernetes cluster. So it can really vary. And you can set defaults. Again, in serverless, you won't really have this option, but in like a production enterprise version, for example, you can actually set what defaults are for, like, if you call it just a GPU or anything like that. You can say the default GPU is going to be an L4 or an A100. You can kind of set up all those defaults in Flyte or Union. I'd have to look at what specific CPU we have here because I forget. Also, was anyone able to sign up? I know I'd passed through the GitHub handles. If you're coming here later, still having issues, join the Slack channel and let us know there. And again, apologize for the authentication issues during the workshop. Definitely not the best time for it. Any other questions from anyone? What was the most interesting thing for people? Had anyone built or deployed a model before? Like, I know when I was messing around a lot, like learning machine learning, to go through a lot of resources and like train and fine tune a model, and then deploying it's a little bit different. So we saw a couple different ways. Again, it was very quick, but like pull down a model. We saw how actually to put in scaling metrics in the cloud, which is pretty cool. So it said real-time processing was cool. Awesome. Yeah, and all this code exists in the GitHub. Let me get the link again. So you also might want to set this up to run locally, not just in the collab potentially. Share this again. So if you actually want to do that real-time running with the webcam like I did here, you could pull down that GitHub repo locally, install the requirements, and then run it here. Again, we're not running on a GPU either. This is, in fact, we're not even using the like processing cores, like the GPU type cores in the Mac. This is all on the CPU. So it's a little choppy here, and I'm streaming and stuff. Probably doesn't help with it. I think if I actually set this to run on the, I forget what they're called. Why am I blanking on the names for the M chip cores? You can actually run with that as an accelerator. And here we're not, and plus streaming and stuff like I mentioned. So this actually probably would run pretty fast if we did some other optimizations. We also didn't really do a lot of optimizations on our model. So you can look at doing like quantization or pruning, converting it to a different runtime. So a popular other file format is called Onyx. There's other ones like TensorFlow Lite, or now it's rebranded to TensorRT, I believe, or RT Lite, which can make your model even more efficient. So if you are running this on an edge device like a Raspberry Pi without any accelerator, that should help a lot too. Someone said, does Union support fractional GPU allocation for container workflows? We do have some fractional GPU type things built in. I know we're working on some more. And then also you can use libraries that do that inside Union. So we have customers that use Ray, which is a library for fractional GPU usage inside of Union as well. But built in, let me see if I can find in the docs real quick. I should mess around with more of the fractional GPU stuff myself. So I haven't in a while. Let me find this for you. I can bring this in to the tab here. So we have in this section, I believe, is some of the fractional GPU. Let me find what I was looking for. Yeah, because I think we have it where you can do. I have to catch up on this myself, doing this live. Yeah, I believe I'm trying to find the part. Oh, here. So you could do some partitioning on the GPUs here directly in the task decorator. So look at this, if that's what you're looking for. If not, one, I'd love to know what you're looking for, because I know we're working on some more stuff like this that will be coming out in the future. But like I mentioned too, you can actually do this, or you might be able to do what you're looking for with some of those other libraries you might have heard about, again, just directly inside of a Union task. Someone said they're new here. They have an application that processes video streams from a camera in real time by YOLO OpenVINO. OpenVINO is Intel's kind of optimization / deployment framework for computer vision models to run on Intel chips, I believe. It's open source, I think, so it might go to other chips now too. Um, it is real to run this application on CPU, not having a strong, I think GPU is maybe what they meant to say. They understand it depends on the CPU itself, but is there any advice on the implementation of such services? So I think you're just asking, basically, can you run like lightweight models, or what models are good to run on CPU only without GPU? Yeah, so like OpenVINO is a good one to start looking at. Qualcomm has one too. I forget what it's called. Basically, you can take these models, and it should already be a pretty lightweight model probably, and then you can do like quantization and optimizations for specific chipsets using some of these frameworks. Like Qualcomm has one. I forget what the name is. If you look up Qualcomm optimizer, it should come up. And then OpenVINO is one for Intel. So you're kind of already on the right track. I think just you can start with other model types like I'm not sure if you're using YOLO, it sounds like, which is already a pretty lightweight single stage object detection model. And then you could look at how to quantize that if you haven't done that. That's kind of the next phase I look at. Like, can I quantize that model, which kind of is just compresses that model? And I know even without doing a ton of fiddling, you can use just PyTorch has quantization methods built in. And when I was doing this a few weeks ago or a month ago for a single shot detection model, so kind of similar to YOLO, another lightweight one, I was able to compress it with like 60%. You're going to lose some of the accuracy there. So it does depend on like your application, like the balance of accuracy and speed. Unfortunately, you can't balance all the things for efficiency, speed, and accuracy. You're kind of doing trade-offs between all those different things. And quantization is a great start. See how that works. And then you can also look at, just like you're already using OpenVINO, that's a great step, and different runtimes. So I think OpenVINO is part of that runtime thing, but you could also look at Onyx is another popular one, TensorRT, and there's a few other ones, but I think OpenVINO, and then if you're deploying on a different type of CPU, you could look at Qualcomm's as well. So there's never a one silver bullet solution for that, unfortunately, from my experience. Someone said, if you want to have one very small model, look at raw data, then send interesting info back to the cloud. Do you have a session on that? I don't yet, but actually, I am building a project like that. So there's cool use cases right now. Like visual language models are really, really awesome. And there's some really cool use cases right now where you might have a lightweight object detection model, kind of like we built today. And then let's say for our project purpose, like you're in a warehouse and you want to send up images to a visual language model to understand if people are using like PPE or other like protective stuff they should be, or they're not in zones that they shouldn't be in. What you can do is use a object detection model on the edge, and then only when something is happening there, then send up a frame to like a visual language model or a more advanced model to get kind of the full what's going on in the scene. So you got a really, really efficient lightweight model. Says, oh, a forklift is in the area. Now I need to send up this picture of the forklift and all the workers to a visual language model. Then I can get feedback of like, is everything happening or is everything correct in the scene or not? So there's a lot of cool projects like this. And this actually could be like the foundational step. Like you would fine tune your model on something like a forklift or whatever that is for your use case, and then send it to visual language model. That might be kind of what you're asking. So instead, is there any reason we couldn't run this locally rather than on Colab? How much more difficult could it be? So it's not very difficult. You should be able to run this locally for sure if you've set up an environment before. The reason why I use Google Colab is it makes it way easier for running workshops. You never know what people's environments are going to be like. You never know like what version of Python they have installed. Do they have PyEnv? Do they have UV installed? Hopefully, with more people adopting UV, it will make this easier. But as someone who's run a lot of workshops before, trying to get people to set it up locally, you just run into way more problems. So Google Colab makes it really, really easy to run the workshop. But I recommend you go run this locally if you want. And you have the GitHub repo, and you can just run the UV or pip install the requirements in your local environment. And then there's even the tutorial notebook that you can go through locally, or you can run all those commands that were in here just in your terminal if you want. So I purposely made these to be able to run locally as well, with the structured code. That's why it's not just like in a notebook cell running it. It's actually kind of formatted, hopefully in a pretty pretty good way, like how I would structure my actual MLOps project. So you could take this down, clone it down locally, run it all, and edit the code, which is totally what I recommend. Like if you're actually building your own project and want to build your own object detection model, I totally recommend that you clone this down and do your development locally for sure. And you can even, like I mentioned, run the commands like when we kick off this job. If you have a GPU or something, you can remove this remote tag, and this will run the workflow locally before you kick it off to like the cloud job, which can make it really easy for debugging. Like that's one of the things where you can save a lot of time. But if you have a heavier weight model, like it actually might even be okay for the mobile net backend. It might just take a long time to train the model part. So maybe it wouldn't save you a lot of time there. But you could replace this with like a lighter weight model, a small sample of data, which we have a pretty small data set today. But if you actually have production data set, you could just sample that data set, basically debug and build your pipeline locally, and then add that remote tag, and then you kick off the pipeline remotely. So great question. Totally recommend, if you're going to spend some time, do local development. That way you'll have your state and stuff always saved. Collab, basically, if you refresh even your if you have your copy, if you create a copy in your drive and you edit code and directly in the code cell, that should stay there. But I recommend doing local development and then actually editing like the workflow and task files in those folders. Someone said, how do they know they signed up? Yeah, you should get an onboarding email. So I will double check with engineering what's going on. Like I mentioned, unfortunate timing for an outage. If you don't get an email right now, try to sign up later or bother me later. And I think you had shared your Slack or your GitHub, Jeremy. So I pass it on. I will go look and see what's going on there a little bit later or right after I get off the stream and see what's going on there. And the other person talking about the optimization piece, they said they already have nano optimized models, int 8, etc. It was a question about some patterns of app or some open source examples, some examples of pipelines for optimized app working. Yeah, I'm sure there's some other examples that's on my list to build too. So kind of like we did today, but instead we can have another workflow kind of after this one. It could be part of the same workflow if we wanted, but I would maybe make a separate workflow that would then pull in our pre-trained model here and then do a quantization and evaluation piece there. It could be another workflow that you add in. It could be part of this workflow too. If you wanted to just have one pipeline, you could get this fine-tuned model. You could save that as an artifact, and then you could do the quantization and save that as an artifact. But I would probably have it as a separate workflow, just so I could rerun this, get a good trained model, and then I might be rerunning the quantization workflow over and over again. And usually, if I know I'm going to be running stuff over and over again, doing some sort of hyperparameter tuning or something like that, then I want to have that workflow run as quickly as possible. And I would just have this one and then the other one that I could go and rerun. Any other questions before we wrap up the stream? I got to wrap up here shortly anyway, but I still see there's people here. So I'll wait around for a few more minutes to see if any other questions come in. Otherwise, I totally recommend, again, I know you weren't able to run this probably if you couldn't sign up. So apologize. Hopefully you'll want to come back and run this and maybe build your own data set. Also join the Slack channel. I posted in LinkedIn comments too. Join the Slack channel and say hello there. There's an introduction channel, but there's a lot of other stuff too. Like if you just want to talk about MLOps, also interested in talking about the AI books or anything like that, that's going to be in the Slack as well. And I'm pretty active in there as well. So if you have any questions, post them there. And if you still don't get the sign up or anything like that, let me know in there as well. There's a channel called Union Support, so it'll be a good place to post that. But you can also just DM me. But if you put it in the channel, then I can tag in other engineers without me just DMing them. So it could be helpful. With that, no more questions coming in. People are saying thank you. Awesome. Thank you, everyone, for being here. And thank you for talking in the chat. It always makes it way more fun for me. These are really good questions, really good feedback. Hopefully you had fun, even though I think the sign up broke for maybe everyone. Hopefully you still had fun. There's still people here, so you must have had some sort of fun or been learning something new. Hopefully you enjoyed it in some capacity. And I'll see you again at another workshop or another talk or something like that, or hopefully hanging out in the Slack channel. With that, I'm going to wrap it up. So I'll talk to you all later. Say hello to me in one of the other places that we connected.